in sections 2.2 and 2.4, I'm sorry, 2.3 and 2.4, our goal is going to be building out our definition for sine, cosine, and tangent away from being linked to these right triangles and into a more broad definition of how we can define like these sine, cosine, and tangents. So to do this, we need to first start to recognize angles that we can't put into a right triangle. So that's going to include angles that are even bigger than 360 degrees and angles that are negative. So we need to be careful about kind of how we're going to define these things. How many of you guys are at least passingly familiar with like skateboarding or snowboarding and heard this term like doing a 540? So when you do something like a trick, a skateboard or snowboarding trick like a 540, what you're doing is 1.5 rotations in the air, correct? Great. Hold on a second, I have something for you.
Thank you.
You're welcome. So the question is, how do I draw a 540 degree angle? We can. We can. So this is how we're going to do it. Is we're going to embed this angle in the xy axis. We're going to fix one arm of our angle to the positive x-axis. We call this part the initial side. And we're going to rotate the other arm of our angle from the positive x-axis counterclockwise until we've covered 540 degrees. So there's 90 degrees, 180 degrees, 270, 360, 450, 540. So there is my 540 degree angle. Yes. We're going to actually address that in a moment, Mark. So just, if you can hold on to that idea. Yeah, I'm actually going to answer that, but it's just going to take me a minute to get there because I want to do a little bit more before I do that. But that's the absolute obvious question to ask right now is why not just call this 180 degrees? Because it appears to be in the same place as a 180 degree angle. And that's an important observation and something we're absolutely going to touch on in just a moment. So we call this other side, we call this the terminal side. You know, like maybe you just had like a little bit of a situation going on there. You know? Did anybody see what he had for lunch? Oh, that would do it. Okay. So, if we want to talk about, yes, of course. If we want to talk about a negative angle, we can describe a negative angle using this same idea. So again, we start with our initial side on the positive x-axis, but instead of rotating clockwise, we're going to rotate, rotating counterclockwise, we're going to rotate clockwise. So 90, 180, 270, 360, 450, 540. So for positive angles, we're going to rotate counterclockwise. And for negative angles, we're just going to rotate clockwise. So Mark made the observation just a moment ago when we drew the picture for 540-degree angle. He asked, why not just call this 180 degrees? Well, we have a definition here that says for something called coterminal angles, these are angles with different measures but have the same terminal side. i.e., to Mark's observation, 540 and 180 degrees are coterminal. And coterminal angles are going to have a lot of properties that we're going to see a little bit later. But as you might guess, basically it means they're going to be the same angle, right? If we say they're coterminal, anything that's going to be true for 540 is going to be able to be true for 180. So, does that make sense there, Mark? And we're going to see when we look at the graphs of these trig functions, you're going to see repeated behavior because after 360 degrees, everything just starts over again. Because of this, what we're observing here with the coterminal angles is after you do one revolution, you're getting the same stuff you saw the time before, right? Is everybody okay with this idea? We'll talk in much greater detail about the graphs of trig functions when we get there, but this idea of coterminal is really interesting, or I shouldn't say interesting, it's very important. So, how could I check to see if two angles are coterminal? Or how could I find angles that were coterminal to a given angle? What would I need to do that? Great. So we can say that for angle x, any angle coterminal to x is of the form x plus 360k, where k is just some value of an integer, so a positive or negative whole number. So ostensibly, what JJ said is if I just keep adding 360 or subtracting 360, I'm going to keep getting angles that are coterminal to the original angle. So to check if two angles are coterminal, so let's pick an obvious example here. So if I want to know if 180 and 540 are coterminal, basically what I want to do is try to solve this equation. And if the solution to this equation is an integer, then yes, those two angles are coterminal. If the answer is a decimal, no, the two angles were not coterminal. So if I subtract 180 from both sides and divide both sides by k, or I'm sorry, by 360, I get that k is 1, which is definitely an integer, so they are coterminal. Yeah, so that z-looking symbol is the symbol we use for the set of integers. So, yeah, that was, I probably needed to mention that more clearly. Yes, that is what that symbol is the set of integers. Looks like a z. with a double bar through it. So let's ask the question. Are these two angles coterminal? Take a moment and check on your own. You might need your calculators. The arithmetic gets a little bit unwieldy. So hopefully we're checking if negative 1,393 is equal to 47 plus 360k. Yes, sir. They are, because k is negative 4. Of course. An integer. So positive or negative whole number. If it's a decimal, they're not. Yes. No, it would work out either way. You would just have gotten positive 4 if you did it the opposite way. But it's still the same check. It doesn't matter. There's no, like saying, is 47 coterminal to negative 1,393 is the same thing as asking, is negative 1,940, or the coterminal to 47. So where you place the two angles does not matter. So that's nice as well, right? Makes it harder to mess that formula up. Good question. Let's check one more. That's fine. It's 21. That's what I was trying to write. So what's different about this? Okay, so what kind of angle or angle measurement? Yeah, these are radians, right? Notice I didn't write radian, but because I wrote them in terms of pi, you should recognize that that's obviously what I'm saying. So if I go back to my coterminal angle formula, what needs to change if this is in radians? The 360 should change into 2 pi. Right? We remember that 1 pi is 180, so 2 pi is 360. Mark, you stretching? I'm sorry, what? You mean into degrees? You could do that as well. This is a little bit, I think, less converting, but you could do that. There's nothing wrong with doing it that way. So we're basically just going to ask or solve, I should say, this equation. Everybody good with that? So when I solve for k, I get that k is 2.5. That's not an integer. Everybody okay there? If I just ask you to write two angles that are coterminal to 53. So you could take and add 360. And Miguel says you could also take this and subtract 360. That's fine. Negative 307. Yep. You could have taken, also, you could have just taken 413 and added 360 again, though, right? Everybody okay with that idea? So when I add just 360, this is basically k equals 1. If I add 360 again, that's like k equals 2. If I'm subtracting 360, that's like k equals negative 1. Just to kind of return back to the formula that we established earlier. You obviously don't need a formula to answer this kind of question. It's simple enough to where, like, you just add or subtract 360 until you see fit. But I just want to connect it back to that. We're still doing the same thing as that formula we listed earlier. Did you guys feel okay about constructing angles now and determining whether angles are coterminal or not? Okay, very good. That's going to close that section. We're going to move on to section 4. So you notice that what we did in the previous section is we expanded our definition of what an angle could be. Remember, in geometry, we couldn't draw things that were greater than 360-degree angles, right? And even angles greater than 180, we had to be very kind of careful about how we were kind of describing that. We can now do that quite easily. And not only can we describe angles between 0 and 360, we can describe an angle of any measure we'd like, positive, negative, as big as we want or as small as we'd like. So we need to now adjust our definitions of sine, cosine, and tangent because we're no longer stuck dealing with right triangles. We have this new definition of an angle, so we need to abridge our definitions of sine, cosine, and tangent. So let's say we have our xy axis here. And let's say we have our angle. Our initial side is always here. It's on the positive x-axis. And our terminal side is here, still in the first quadrant. I'm going to call that angle alpha. So that's the Greek letter alpha. Kind of looks like the Jesus fish. Okay. And let's say we have a point on the terminal side. That point I'm choosing arbitrarily right now. I'm going to name that point P, and I'm going to say that it has coordinates x, y. Everybody okay with this so far? Okay. So notice here that if I draw a vertical line from that point P down to the x-axis, what I've done is I've created a right triangle, right? Can everybody see that? What is the side length, or this side length for that right triangle? How far is that? X. Very good. Notice that because we drew this vertical line from point P that was x over, that means that side length on the x-axis has length x. What is this side length going to be? Y. And then what is this length going to be? The square root of x squared plus y squared. How do I get the square root of x squared plus y squared? What was that? Pythagorean Theorem. And to make our lives easier, I'm going to just call that length r for our definitions. Okay. So, now if I want to take sine of alpha, I can say that my sine of alpha is y over r. Similarly, cosine of alpha is going to be x over r. And tangent of alpha is going to be y over x. Cosecant of alpha would be r over y. Secant of alpha would be r over x, and cotangent of alpha would be x over y. And at first glance, you might have said, Mr. Kulik, this is the same right triangle definition that you've given me before. Like, what the heck? You told me this was going to be different. It is different. Because we are not defining this in terms of a right triangle. We're defining these values in terms of a point on the terminal side of our angle. It is fundamentally a different definition, and you'll see why in a moment when we do an example. I'm going to pause here because I still see a lot of people still copying, so I'm going to slow down here for a minute and let everybody kind of catch up. So we have that point, the point negative 3, 4, lies on the terminal side of angle theta. Find all 6 trig ratios for theta. So I need to find sine theta, cosine theta, tangent theta, and then cosecant theta, secant theta, and cotangent theta. So to evaluate sine of theta, I'm going to use y over r. I know what y is right away. That's 4. How did I calculate r? Yeah, it's the square root of x squared plus y squared. Everybody okay there? So cosine would be what? negative 3 over 5. Tangent would be, negative 4/3. Cosecant is just the reciprocal of sine. Secant is just the reciprocal of cosine. And cotangent is just the reciprocal of tangent. And what do we notice right away? Look at the answers that I've gotten here. Got negative values here. Was this possible to do when we were looking at a definition inside of a right triangle? No. We can now get negative values and negative outputs for sine, cosine, and tangent. Is everybody okay with that idea? Just to kind of demonstrate this, so 4 negative 3 would be over here, correct? Would be this kind of a positive angle. Everybody agree with that? So let's just make something up, like 300 degrees would be in that quadrant, right? We've gone 90 degrees, 180 degrees, 270, 300 would be somewhere in that quadrant. If I fire up my calculator and take cosine of 300, what kind of answer am I suspecting to get? A negative. A negative. Make sure my mode is degree. Okay. Cosine 300. Oh my God. Who is confused at the picture I've drawn? Abby, you were making faces. Yeah. Well, be louder if you see it. What did I do here? Yeah, I graphed the wrong thing like a giant stupid head. So let's say maybe that's 150 degrees. Right? That's about right. Or a plausible value for something in that quadrant. And we're getting a negative answer. There we go. Everybody okay with that? So you see that your calculator has been already using this definition for sine, cosine, and tangent because you are able to get negative values for sine, cosine, and tangent. Your calculator was ahead of the game. You got that right. If I restricted everything to happening in the first quadrant, that's essentially our old definition for sine, cosine, and tangent that was linked to side lengths of right triangles, where all the side lengths must be positive. As soon as we expand our definition and allow that angle to lie in any quadrant, we now open up the possibilities for negative values for sine, cosine, tangent, etc. We're going to stop here. For next time, I'd like you guys to do 43 to 46. That's not so bad, right? We still have to finish section 4, so I'll have more to do there next time we meet, but that's enough for today.